All right, so our next topic that we're going to consider is forecasting techniques. And I encourage you to check out the chapter in the textbook related to this. It has a lot of extra details. We're just going to really focus on the heart of it and then talk about one other possible extension that doesn't necessarily have to be part of forecasting, but can be generally part of modeling that we wanted to talk about with regression. But in general, right, forecasting techniques, what are we doing? We're interested in thinking about predictions, right? About what future values are going to be. This is primarily used, right? When we think about forecasting, we're usually thinking about there being a time component. And so we primarily focus on time series kind of data. We don't always have to have time series data, but that's a way that we can make a forecast. Oftentimes we think about some time series data. And I remember in grad school taking an entire class just about time series econometrics, and so the sophistication of the models, if you go into an area like finance that might be looking a little bit more like forecasting, then maybe you might want to dig a little bit deeper into this. But again, for our purposes, we just want to touch on it very, very briefly. So what do I have here? I have a picture of gross domestic product through time, right? And it's clearly got this upward trend, as we've alluded to earlier in this class, and I've even got some data. And so clearly this is, right, what kind of data are we looking at here? This isn't cross-sectional, this isn't panel, this is time series, right? Because we've got this time component. It's going through time, and notice that it's measuring different quarters in the series, starting with 1999. And it's got the GDP in billions, and so it's pretty clear if we were going to fit a linear trend to this, it would probably do a pretty good job of capturing what's going on with an upward linear model, right? But some of the things that we can do with our techniques, some of the things that we might want to think about when we're looking at time series data are different things like cyclical effects or seasonal effects, right? And so we want to make sure that we understand the difference between those two. Does it look like there is a seasonal effect in this data? What do we mean? What's the difference between a seasonal and a cyclical effect? A seasonal effect is something that follows a specific pattern and on a specific timeline, right? And so you think about the seasons of the year. That's the whole idea, right? That you've got summer, fall, winter, spring. Well, actually, what they do with this GDP data and with a lot of economic data is with those natural weather patterns and the natural pattern of certain holidays, that you actually do see this periodic repetition from one year to the next in certain times of the year. That's what seasonality is, right? And so what they actually do is they do some seasonal adjustments so that we abstract from those highs and lows that are related to the seasons, and we get a better underlying picture of what's going on. But in general, right, seasons, we tend to think about those as being not that long of a time period, but some periodicity, some periodic repetition of a pattern. That's different from a cyclical effect. Now that typo's fixed. A cyclical effect is still about an up and down pattern in the data, but a cyclical effect is not necessarily going to be restricted to a short time period or a short window that repeats itself, right? And so, for example, if we look at this GDP data, right? So if we tried to fit let's go ahead and try to fit a long-term trend just by doing some little bit of ocular regression, right? So it looks like what we have is that we've got some times when maybe I need to push that up just a little bit, right? We've got some times when our economy is producing above the trend and sometimes when it's below the trend. Usually that's after a recession, right? And then we've got other times when it's above the trend, and then we had this great recession in 2008 where we were below the trend, and we maybe are a little bit above it now, right? So we've got this up and down nature. There's a cyclical pattern, but notice that this stretch of up and down totally is a different time window than this one, right? This was a very short, just a couple years up and down, whereas this up and down and back up has stretched out over a much, much, much longer time period, right? So seasonality, we think about it as a year to year. We're always seeing this effect. And a cyclical, it's still got the up and down sine wave sort of pattern to it, but the spacing of it doesn't have to be consistent from one top to bottom point, right? But again, just these are some things to be generally aware of that are part of forecasting. The main thing that we want to actually do in Excel related to forecasting has to do with developing a moving average, right? And so we can talk about moving average models. It's a way when we have a whole lot of variation in the data. This is often referred to as a smoothing technique because it's going to reduce some of the extremes when all we're doing is, if we take a quick look at this basic equation of a moving average, to find a moving average value of a variable, we just take its value in the last time period, today, and the last time period, and we just average the two, right? That's where the name comes from. And it simply moves along from one period to the next. We have all of this data, and so a moving average is just going to take these two and average them out. And then the next one will take these two and average them out. And so we end up with almost the same number of observations, but rather than having each of those points, we have an average of that point and the last one, and so it just kind of smooths out some of the edges. It reduces some of the extreme values that we'll see. So let's head over to Excel and look at how to implement this thing, and then we can say a few more comments about moving averages. So I have a data file that's up on Moodle called Tablet Computer Sales, and if you just want to pull that up, this is clearly time series data, right? Where we've got weeks, we've got units sold. We can do a couple of things. We can look at it real quick just to see what the pattern is, right? So if I go ahead and select my data, and I just want a little, a nice little line chart. Actually, you want to give me a recommendation? Sure, right? Units sold, I did a little scatter plot so it had weeks. We could also, if we wanted to just highlight the units sold, we could do that in a line chart as well, right? Same general picture, right? Just there's some bouncing up and down in terms of units sold, and so maybe that extra uncertainty from one week to the next, we might want to try to smooth it out with what we have a moving average. So we just talked through, right, that the moving average version of units sold, what that's doing is that's simply, right, we don't have an undefined for the first value, but undefined for the first value. But basically what we're doing in week 2, right, the moving average value in week 2 is equal to the value of week 2 plus the value of week 1 divided by 2. We're just averaging the today's or this week's units sales with last week's units sales, right? And notice that it's a big drop from week 1 to week 2, went 88 all the way down to 44. If we just average those two together, right, it would smooth out that extreme a little bit, right? And now once we have this formula, we could go ahead and copy it all the way down. And if we glance down this, notice that, right, it's not quite as extreme values as what it was before, right? At the bottom of this, real quick, let's calculate two things. Actually, let's use the hotkeys for this. Let's calculate two quick things. Under the formula, oh, gotta move that cursor to the bottom, and then under the formula tab, we can real quick insert average. And sure, average. And then we could also, under the formula tab, I think this is an easy option, not average. I don't want average. Formula. Nope, it is automatically trying to do that. Let's. What I wanted to look at was the spread of the data. So I'll just type it out. Standard deviation, not a big deal, right? So with our original data, the average was 60.64, and the standard deviation was 15, right? So think about what the coefficient of variation is. Notice what happened when we take the moving average. It's nearly identical, right? Remember that we don't quite have a previous observation, and because that first week was a little bit higher, was one of the peaks, that our average is going to be a little bit different when we calculate the average of the moving average, but it's still very, very close to it. The main thing I want to point out is look what happened to the variability. Look what happened to the standard deviation when we added this moving average. If we wanted to look at these as a comparison, right? So I deleted out that little tick mark because that was giving me some hiccups in this. But if I highlight my data again and I just look at a little top-down comparison of what my original data was in blue, notice this in blue, same line as before, but now we're adding in the moving average in red. And notice that all it's doing is just kind of smoothing out the extremes of this thing, right? Those peaks, those troughs, the line in red just kind of smooths them out, so we get a little bit more of a smooth sense of what's going on from one week to the next in terms of our sales. It kind of reduces that extremes. One other way that we can pretty easily do a moving average, what we just talked through was a moving average, which is a 2-week moving average, right? But go ahead and delete all that. It's not working for me today. We can pretty easily do a moving average as well under the Data tab. Data Analysis, when we bring that up, there is an option called Moving Average. And if I bring it up, I need to highlight my initial data. Again, I'm going to highlight it with the label, make sure I don't pull the average below, and I'm selecting the labels in the first row, and now I've got to tell Excel where it's going to put those moving averages. So this is a little bit counterintuitive, not counterintuitive, but this is a little quirk of Excel. I highlighted this with a label, but for my output range, it's where they're putting the data, not the label, and so I'm starting it at C4, right below where the label was, because it's just this little dialog is only going to put the data. One more thing I have to do, the interval. So what we were doing is we were doing a 2-week moving average. The interval option in this dialog box is asking how many previous time periods do you want, or how many time periods do you want to include? Today's and last week's. So that's 2-week moving average. I enter a 2, and boom, 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 boom. Same data as before, right? So same data as before, and notice that the picture that we had looks identical. I point that out because we don't have to just do a 2-week moving average. We could do a 3-week or a 4-week or a 12-week moving average, right? We could do much, much higher moving average. Let's just go ahead and real quick adjust it to a 3. And, yep, overwrite it. Notice a couple of things happened. Number one, I lost one more observation, right? Because for the first 2 weeks, I don't have 3 observations that I can average together for those first 2 weeks. My data series is only going to start in 3. But notice what happened to that line in red, right? It got even more smooth, right? Because, again, it's including even more variables. I didn't have my average and standard deviation, but I should be able to pull those to the right. And what it should show is a slight... No, because it's getting mad about those NAs. Notice that the average is, again, roughly the same. On average, it's the same value, but it's just reducing the amount of variability that we automatically see. Let's go one more extreme jump. What if we did a 5-week moving average? So think about how ridiculous that might be, because we're going to lose a whole bunch of data. But notice how much more smooth that little line in red is. And then again, right, it's getting mad about the NAs, but the data is clearly saying the average is about the same, but that standard deviation, boy, cut it in half. But think about, is that the right way to model this, right? It's always going to depend. So there's a little bit of art with using moving averages to think about the forecast, because you've got to know what you're doing and who's using the information, right? If you are trying to forecast the sales from a store, you got to know what kind of industry you're working in. 5 weeks ago, is that a ridiculously long time? Are you over smoothing this, right? And so there's always these kind of considerations, but it is one way to kind of reduce this uncertainty. We can hop back to the spreadsheet, and I can write out some things with a formula. This is a 2-week moving average. This is the equation of a 2-week moving average. What do you think the 3-week moving average equation would look like? Right, so again, think about the pieces that are here in this 2-week moving average. We had today's value, and then we used last week's value, so we had 2 values, and we were averaging them by 2. If we were going to do a 3-week moving average, then, right, xt plus xt minus 1 plus xt minus 2, right? We're going today and then 2 previous time periods, and to average them, we just divide by 3, right? So more generally, right, it's not a big deal, right? The other thing that we wanted to think about that sometimes happens in moving averages, right now, this is a moving average, but the information today and the information from last week, they're getting the same punch. They're having the same impact on the average, right? So one of the things that sometimes you might see is they might put some weight. They might put an adjustment. And so they might add some coefficient in front of the x's to kind of reduce how important today is and how important yesterday is. You can play around with the balance between what those are. So I'm going to write out a long version of this equation, and then you see if this makes some sense to you. All right, so I can do theta xt plus 1 minus theta xt minus 1 divided by 2, right? So in general, that's a t minus 1 down there, right? And what I need to know is that these two pieces right there, right? I've got my theta in my x, and I've got my 1 minus theta in the other, right? If I add those two things together, what do we have, right? So I've got theta plus negative theta. My thetas are actually going to cancel out 1, right? It's just a way to weight today and yesterday's importance. So think about this for a second. If theta, oops, I need to make one adjustment to this equation that was incorrect. I need to erase the divided by 2. If theta is equal to 0.5, could you write out what this equation represents when theta takes on a value of 0.5? Oop, I was using the wrong name for the Greek symbol. That was not theta. This is theta. The other one was a different Greek symbol. This is theta that we want to use, right? So, but again, right, point is, if we have this with 0.5, hopefully you carried out this math and you found that when theta equals 0.5, it means that the weight that's being assigned to each of the values, today's week and last week, are the same, right? But what this more general functional form does is it allows us to be a little bit flexible with some of our values. Let's go ahead and do another calculation. What if theta took on a value of 0.75? Can you again rewrite this equation, but now with theta taking on a value of 0.75? And then think about, what does that represent? And we were just looking at a 2-week moving average. We were when we include this more general theta version of the equation, what this is a 2-week weighted moving average. But you could make this thing much more complicated, where you could do 3, 4, 5 weeks, and you could have the weights be a much more complex, right? There's tons of complications that we can layer on to more sophisticated forecasting that are probably beyond the scope of this class, right? And so again, there's this exponential smoothing model that looks a little bit different. There's got some similarities to what we just talked through, but it's a little bit different. Again, I don't want to jump into the details. You can glance through what the chapter says about this, and again, depending on the direction that you want to head, you might get some more exposure to these in upper level classes. Maybe you won't if it's not the direction that you're heading, but we just want to kind of make some general introduction so that you are generally aware of some of the ideas that are going on here. The other thing that we wanted to talk about, and again, this isn't necessarily having to do with time series. We can apply this for cross-sectional or panel data as well, but we wanted to do a little bit longer discussion about the use of dummy variables in modeling. It could be used in forecasting, or it could more generally be used in modeling. And so we just want to say a few things about how we could incorporate that and look at some examples. Recall that when we have dummy variables, they always take on a value of 0 or 1. It is a binary variable, right? There are two outcomes. It's a 0 or a 1. So, and again, that's mutually exclusive. You can't have one or the other, and it's got to cover all possibilities. And so the way that we write out a dummy variable, it's good when you are creating dummy variables to include in their name the thing that you are identifying. So for example, a dummy variable called dummy college degree would be identifying those individuals who have a college degree. And we just have mathematically, right? So the way that we would operationalize this dummy variable is the dummy college degree variable. That's going to be a column in Excel. It's going to take on values of either 0 or 1. It takes on a value of 0 when that person does not have a college degree. It takes on a value of 1 when that person does have a college degree. And so again, we're saying that this is a dummy variable that identifies someone having a college degree. Two other variations of this, right? So this is clearly a yes/no college degree, but we can also have something like gender, that where there are our data set may include two outcomes for that variable, male and female, right? That's a pretty common one, but you can think of a lot of other categorical variables that have two different categories, right? We would not want to have a dummy variable on gender. Rather, we would want to have a dummy variable on male or a dummy variable on female. Remember, right, that we want then the name of this dummy variable to identify the thing that the one is identifying. So if we just wrote out the word dummy gender, it's not clear what one is going to be identifying, but dummy male, right, that language, the way that we've named that variable indicates the thing that we're identifying with the one is a male, right? another variation of this. So we've thought so far about college degrees and genders as being categorical variable, but how about income, right? What kind of variable is income? Income is clearly a ratio variable, right? It goes from 0 all the way to a very, very, very big number, right? But it's got this ratio. It is a ratio variable because it's continuous and it has a true 0 and all of these things. However, we could still create a dummy variable based on that, right? So I've got a dummy variable here that's a high tax bracket, right? So marginal tax brackets in the US, the highest tax bracket starts at 500,000. And so what I can do is I can create a dummy variable that identifies whether or not an individual is in that highest tax bracket. It takes on a 0 if the value of this continuous variable income is less than 500,000. And then the dummy variable for high tax bracket takes on a value of 1 when income is $500,000 or more. This should not have that inequality there so that we've got some mutual exclusivity between those, right? So in general, right, your income can fall anywhere on the spectrum. It's a continuous variable, but what we're doing with this dummy high tax bracket is we're saying right at that clip of 500,000, we're dividing it, and all of these individuals are going to be zeros, and all of these individuals are going to take on a 1. Again, it's most natural to think about dummy variables for categorical variable, but we can also take any continuous variable and create a dummy variable based on forming categories of that continuous variable. So what I want to do is I've got another data set up in Moodle having to do with salary. And so I'm going to bring that up, but what I want to go through is estimating current salary as a function of education, estimating current salary as a function of this dummy male variable that we're going to create, and then this is called a dummy interaction term down here, right? Where with this last model that we're going to look at, its current salary is a function of the dummy male variable, the education variable, and those two variables multiplied with each other. I'm taking education and I'm multiplying it by dummy male. And again, this last one is called a dummy interaction term. So let's hop over to Excel and estimate these three equations and then talk about what they represent, what the outcomes represent. Okay, so the data set is called salary data updated. We've got a bunch of cross-sectional data, right, where we've got couple of different variables, right? We've got current salary, we've got beginning salary, we've got previous experience measured in month, and we have education measured in years. And what I added to this was a gender variable. So I've got a bunch of M and F for males and females. Current salaries measured in dollars, ratio variable, right? And then the other one that we carried about was education. With the way that this education variable is created, it's a ratio data, right? It's continuous because it's got all of these different years, but it looks like they're counting different years, so we can treat it as if it was a continuous variable. Gender, categorical, where we've got, for this data set, we've got males and females are what's being identified. Remember, the first thing that we had to do, or the first model that we were going to estimate was current salary as a function of education. Let's go ahead and estimate that in regression real quick. So data analysis, I go to my regression and my output range, right? I've got current salary. So I'm selecting that as the Y variable. Is that the independent or the dependent variable? That's the dependent variable. And then my independent variable, the thing that I'm measuring in my X's, that's education. And so D3 through the end of the list, I included my labels. And then where do I want to put it? So for an ease of comparison, let's go ahead and put this next to the data. So I have moved it right over here in G3. And go ahead and click OK. And then we can talk about what are some of the main things on regression that your mind or your eye should be jumping to. Again, your R squared, right? 0.316. Can you explain what that represents? Your coefficients of the intercept in the education variable, negative 13,693 and education 3,579. Can you explain what those variables represent? All right, so hopefully you've had some practice with that and that you feel good about all of those. The main one that I want to focus on is the education, right? So that education variable, remember, the coefficient represents when we have one more unit of the X, how much the Y changes by. What was X? What was Y? Our X was education, and our Y, our outcome, our dependent variable, was salary. So this is saying when you have one more year of education, this 3579 is how much salary is going to change by. Having one more year of education boosts current salary, on average, by $3,579. In a sense, that's the payoff for going to college, right? You get one more year of education. This is an estimate of what one additional year of education does to your current salary, and realize you're going to have that all your life, right? So you can think about getting a 4-year degree. If we took this value and we multiplied it by 4, that is the average impact on your current salary of going to 4 years of college, right? So again, is it worth it? Think about the price you pay for college. It's pretty hefty cost to go to college, right? But we can think about what it is. I want to point out that this data is a specific data set that's about a specific set of employees, and so it is not a generalization about the overall population. I want to emphasize that again, that we're about to look at some gender stuff, and even with this education stuff, that this is for a very specific sample that is not representative of the overall population. This tells us for this group of people what the return to college is, not necessarily overall for the overall population what the return of education is. On education is. The other thing that we want to ask is, are these two variables statistically significant? That's the other thing that your mind should be looking at, the p-values, right? And again, using an alpha value of 0.05, it looks like the intercept, it's right about there on statistically significant. It's not quite statistically significant at 0.05, it would be at 0.10, but again, this intercept term, remember, thinking about what it represents, look back to this education column. You scroll through the whole thing, there are no zeros, so this value itself, it's kind of a ridiculous point because it's outside of where our data is. We do the estimation, it's not quite statistically significant, but even if it was, that's not where anybody is, so it's not really that useful of a piece of information. The education coefficient is much more useful and very, very, very low p-value. So clearly that's got statistical significance even at the higher standard of alpha equals 0.01. That's still definitely hitting home statistical significance. And the other thing that I wanted to point out is, notice that with this lower 95%, upper 95%, right, that is putting a confidence interval, right? And you remember confidence intervals from a few topics ago. It's the confidence interval around this coefficient estimate. So our coefficient estimate, our point estimate is 3579, but our interval estimate, a 95% confidence interval, 2525 up to 4634. Notice that it's a range of values, and this range of values does not include 0. When the range of values on a confidence interval does not include 0, you're also going to see statistical significance. Those things are equivalent ways of doing it. I like looking at the p-values. Most people do, but I know some people like looking at the confidence intervals. If the confidence interval does not include 0, it means it's statistically different from 0. Okay, that was education, and I think the education one's pretty straightforward, but we've got to add one more story. We got to add gender. I'm going to actually do this where I add a column before, where I include, actually I'm going to add 2 columns, and let's put in this new column E, the dummy variable on male, right? So again, I've got gender right here, and it's a bunch of M's and F's. So to convert that to a dummy variable of 0 and 1s, I'm going to use an if-then statement. If this value in G4 is equal to M, then I need it to be a 1, right? Because it's a dummy male, so the males are the M's, identifying the 0, what did you want to do? Oh, I think I need to use the other kind of quotes. Yep, we needed to use the double quotes instead of the single quotes. When we're using text, and we're asking Excel to look at the text, we have to use the double quotes. Straightforward if-then structure. I do that. And if I multiply this whole thing down the list, I get a bunch of 0s and 1s, and I can just visually check. The F's became 0s, the 1s became M's became 1s. That is a dummy male that identifies males with a 1. So real quick, I want to estimate my second model, which was current salary as a function of dummy males. So under data analysis, I've got my regression, and it brings up some of my earlier stuff, right, where I've still got the same Y value, but now in my X value, I don't want education anymore. Instead, I want dummy male. Down the entire list, I've still got my labels. Because I added some columns, I need to make an adjustment with my output range. I need to make it anyway because I don't want to overwrite this. I want all of these things to be together. I want to put it in, let's put it in I-23, so 20 rows below my last one, so that I can look side by side the comparison. And I do that, estimation, and I've got a couple of things that your eyes should be drawn to. The R squared, the coefficient intercepts, the p-values, and so the R squared dropped significantly, right? Remember, in our second model, the only thing that we were looking at was males, whether or not someone was male or female. That doesn't really explain a whole lot of current salary, does it, right? It only explains 5% of the variation in current salary. However, we've still got statistically significant coefficients, right? So both of these coefficients have p-values that are very, very small. So, yep, we've got statistical significance at the alpha equals 0.05 level of significance, right? But I want to think about this intercept coefficient and the dummy male coefficient, 9,295, intercept 26,661. Those are useful. Let's take those values back and write out this to see why they're useful. So I pull this into the slide so that I can write this out. This was the model that we just estimated, right? We've got current salary. I'm going to write out the estimated equation. Current salary. What was my estimate of beta naught? That was my intercept coefficient, 26661. Was it statistically significant? Go back and check. It was statistically significant, and even, right, we talked about this before, that we've got this convention that oftentimes we look at 3 different levels of significance, 0.05, 0.10, and then 0.01, kind of the increasing level of rigor that we're putting on the data or comfort with committing a type 1 error. Oftentimes when we write out these equations, we can use stars to designate the level of significance, right? And that first coefficient that we estimated was a very, very small number. It was less that p-value was less than alpha 0.01, so I can put 3 stars by it, and that communicates, yep, it had the most significant level of, it reached the most rigorous level of significance, the alpha 0.01. That was our 2601, and then the other one is 0.9295. Do we want to include any decimals, right? So we've got 9,000. Is 9,295 very different from 9,295.4? Probably not, right? I think you could get away with not doing any decimals. If you wanted to include a decimal, you might want to include maybe 1 decimal, but I don't think you'd want to go much beyond that. You clearly would not want to include 4 or 5 decimals. Look back though, do you recall what was the level of significance that we had? The p-value for this, right, wasn't it p-value 0.017? I had my number wrong, 0.019, right? If this is my p-value, is it statistically significant at the 0.10? Yes, because that p is less than 0.10. Is it statistically significant at the alpha equals 0.05? Yes, because it's less than 0.05. But notice, it's not significant at the 0.01. It's a little bit higher than that, right? So the way that I would write that is I could write that number and I could put 2 stars by it, which again is communicating pretty succinctly that it's statistically significant at the 0.05 level of it, right? This stars convention of reporting a model is usually pretty standard. Not everyone does it, but a lot of people do. So if you ever see it, that's just, I wanted to point out that if you ever see it, that's what it is. And I also need to include my variable, right? So my variable was the dummy male. How about this error term, right? This error term, on average, the average error term, the error term hat on average is 0. So again, right, I don't need to write anything else here. If I wanted to, I could write +0 because the estimated average error on the estimated error on average is equal to 0, but usually we don't write something that's just a 0, right? We just suppress the notation. And so this is the way that I'd report the model. I can delete those because I know they're statistically significant and I don't want it to distract from my main point of how useful it is to estimate regression with a dummy variable. So here we go. This dummy male variable, though, it takes on two values, right? It either takes on a value of 0 or 1. So real quick, let me write out those two conditions. The current salary conditional on 0 and the current salary conditional on 1. All right, so I went ahead and filled in all the math, but let's talk through it real quick. So we've got the two conditions, right? The current salary, that's what this model is, current salary. And I've got two conditions. Dummy male equals 0 and dummy male equals 1. Remember, if the dummy male equals 0, which group are we talking about, right? We're talking about the females. And we're talking about the current salary of females. When dummy male equals 1, those are the males, right? This is the current salary of males. So all I'm doing is just plugging the value in, right? Recall, when dummy male equals 0, so I'm plugging dummy male 0, I'm plugging a 0 in here, and then just using my estimated values, and I got 26661. Actually, that's the intercept, right? The intercept represents the average current salary of females, right? Now, when dummy males takes on a value of 1, what do we have? Plug a 1 in for dummy males, and then just use the estimated value. So I've got 26,261, that was my intercept, plus 9275.5 times 1, because dummy males equals 1. And that equals 35,936.5, right? So what is that? That is, on average, current salary for males, right? So what do we get? The 26,000, that's on average how much females make. The 35,936 is on average how much males make. Notice, what's the difference between these two values? If you calculate the difference, what you'll see is it's the 9,275.5. The coefficient estimate on a dummy variable represents the difference between the groups. This is saying the males make, and it's positive, the males make current salary on average $9,295 more than females on average, right? So for this group, it seems like there is a gender wage gap. We can use a dummy variable on males to identify in the data what the average difference in wages are between the two genders in the data set. Yeah? That's why dummy variables are so nice. And again, we already looked at the p-values. Is there a statistical significance? Is there a statistically significant difference between the salary of these two groups? Yes, the p-value said there was statistically significant different average current salary between males and females, right? So we had actually done that, and we could have carried that out with a hypothesis testing from a few topics ago, right? But what I liked is all we had to do was just have a dummy variable and run it in regression and look at the p-value, and the coefficient tells us the difference between the groups. And it's specifically looking at how much different the thing we are identifying a 1 is compared to the thing we're identifying with a 0 is. Make sense? We want to add one more thing to this story that makes this a little bit more complicated, this dummy interaction term. So let's go back to Excel and estimate this last equation. All right, so if you recall, we need to include the dummy interaction term, which was just taking the amount of education multiplied by the dummy variable, right? So I'm labeling this thing as education DM for the education times dummy. We could also call this an interaction term. Remember, all we're doing with an interaction term is taking the amount of education and multiplying it by the dummy variable. Think about what this is about to produce. For this male, it produces a value equal to their education, right? As I copy this down the list, though, for all the males, it just reports back the level of education. But for all the females, right, their dummy value is 0, so it reports a 0. So notice that, geez, it looks a lot like this earlier column, except when there's females, it gives a value of 0, right? I don't think that itself makes very much sense, but let's estimate the regression and then the interpretation will hopefully make a little bit of sense. So okay, so let's go ahead, and now we're estimating in this big model. What we're doing is we've got our regression, and we still have our current salary, but now our input range, right? This is why I added the extra columns, because recall, for the input range in Excel, they all have to be next to each other. So I want education, I want dummy male, and I want this interaction term. I want all three of those right-hand variables. So we're doing some multivariate statistics here, right? Or regression, multivariate regression, right? And I go down the entire list to highlight everything of those three variables. I've got my labels. I need to move my output range. What did we move it? 20 down. So if I move it to 43, it'll put it in a good place. And go ahead and hit OK. And what do we got? Real quick, what are some big things that your eyes jump out at? The R squared. Notice the R squared, right? With this model that looks at both gender and education, we explain almost 37% of the variation in current salary. That's what the R squared is telling you, right? We've got, here we go, our statistical significance. If you recall, I've avoided this so much because we only had one variable. But now that we have multiple variables, remember that this is testing, are any of your right-hand variables different from 0? And we clearly have are going to reject that none of them are 0. And so we are finding that our model is telling us something. Here we go. P-values. Real quick, our p-values. So the intercept, not a value that's distinguishable from 0 statistically, but at the lowest level of significance, alpha equals 0.10, the lowest rigor of significance. We've got statistical significance for all of these. We've got the coefficient estimates. Let's go ahead and bring those back in and write out this model and then interpret what it represents. Okay, so we are back into where we've got our alphas, 0.10, 0.05, 0.01. We've got our model, and now we've got the estimated coefficients. Take a second and see if you can write out, again, these two different scenarios. Current salary, conditional on looking at the males. Or no, we looked at the females first, didn't we? Females. And then the current salary equation, conditional on looking at the males. And again, recall that for the females, that's when the dummy male took on a value of 0. For the males, that was dummy male took on a value of 1. See if you can put together this estimated equation for females and males. Okay, so hopefully this is the math that you went through. Again, I'm just using my form of the equation with my estimated coefficients evaluated first when dm takes on a value of 0, right? So 7948, that's my intercept. 1580, that's my education, and then education is a variable. And now I've got the negative 34606, which is the coefficient on dummy male. But for females, dummy male takes on a value of 0, and the 2996 education interaction term. But for females, right, so this becomes a 0. And so this equation simplifies too. This is the equation of current salary as a function of education for females. Question, can you interpret what does this value of 1580 represent? And then also, how about the other one? For the current salary for the males, again, 77948, 1580 is the coefficient on education, but now this negative 34606 is the coefficient on dummy males, but dummy males for males takes on a value of 1, plus 2996 education interaction term, but dummy takes on a value of 1. And so when I start carrying out that algebra, right, 34606 times 1 is a number that I can combine with this other constant term to get 26658. And education, I can combine those terms to 4576. And so what I've got with this is the current salary education, or the current salary equation as a function of education for males. So, can you interpret what the value of 4576 represents here? And so that's the role that dummy interaction terms play, right? The difference between the 1580 and the 4576, that difference is the thing that we estimated the interaction coefficient as, right? The difference between these is almost $3,000, right? That's how much more effective education is on current salary for males compared to females. An experiment calculation for you to do is go ahead and calculate the calculate the current salary for females when education is 16, and the current salary for males when education is 16, and then recalculate when education is equal to 17. So the current salary for females when they have 17 years of education, and the current salary for males when they have 17 years of education. And then if you look at the difference, what you should find is that having more education boosts both of these, both type of workers' salary, right? More education leads to higher current salary on average. But what you should find is that males, the boost to their salary is $2,996 more than the boost to female salaries of having that 17th year of education.